features about those respiratory surfaces that suit them for carrying out gaseous exchange. To begin with, they are moist. So, they are moist. By moist we mean that they are wet. Actually, respiratory surfaces, all of them are wet. Now, this wetness, this being moist, enables the gases to dissolve, and when gases like oxygen dissolve, they easily diffuse for easy absorption. How do you know they are moist? For example, if you breathe on a glass or a ruler or a mirror, like, you'll see some moisture that comes with your breath. That shows that in our lungs it's well moist, so as to dissolve oxygen for easier diffusion, and carbon dioxide too. Well, for fish they don't have a problem because they stay in water, so the gills are already wet. They are well ventilated. What we mean by ventilated is not that they have windows, doors and ventilators, but there is a mechanism that enables, oxygen to come and carbon dioxide to leave. For example, in human beings, we have a ventilation system. That's to say, we breathe, okay? So we breathe in carbon dioxide that has crossed from the lungs, and we breathe in oxygen that has from air, okay? So they are well ventilated. So it happens, you breathe in oxygen, you breathe out carbon dioxide, and that goes on and on. Now that enables these surfaces to keep doing their work efficiently, and all the other organisms, even birds like chicken, actually have a ventilation system that's efficient. These surfaces are very thin. Most of them are just one layer of cells. Only one layer of cells. They are very delicate actually, and that's why you'll find them very well covered within. For example, for mammals, they are well caged. They are well protected within the rib cage. It's not that easy to hit, to pierce through lungs unless if you're intentional, because the rib cage keeps them. For fish, they have what we call a gill cover, the operculum, as we're going to see on. That protects the delicate gills since they are very thin. They are well supplied with blood, so they have a very rich collection of what we call capillaries. Now, these blood capillaries surround these gas exchange surfaces so as to quickly take away the oxygen to the body. Say in my lungs, there is a rich supply of blood capillaries around my lungs, so that all the oxygen that has been obtained from the air immediately goes to my body for circulation. That's why from transport we saw that there's a particular vein that returns from the lungs and a particular artery that goes to the lungs. So they are very well supplied with blood, so as to take away the oxygen and to bring up the carbon dioxide, which is taken away by the ventilation system, and that keeps the diffusion gradient, that keeps the difference in the concentrations. Remember I said these respiratory gases move freely. So meaning the body has to put all conditions that encourage these gases to move freely. So they are well supplied with blood. They are folded or branched. For example, within insects, as we shall see, they have a tracheal system that further divides into tracheoles. Now, this branching allows the surface area, allows an increased surface area for a gaseous exchange. Think about it. What if it was just this? What if it was just that? Well, gases would diffuse across this surface, okay? Because for them, air comes through like that. Of course, gases will diffuse across the surface. Now, let us branch it once, like this. Now, we have increased the space for exchange, okay? So more gases can actually move across this new space we have put, this new surface we have put. What if we further branch it like this? Check. More of the oxygen can now diffuse through this place, so that this remaining part of the body gets as much oxygen as possible. So the more we fold it, the more we create surfaces over which gases can move. What if we even further fold it? We have created another space. Yeah. Now, if you unfold all this space, you're going to see a very large space, a very large surface for exchange, and that makes it more efficient for gaseous exchange. Well, sometimes they are folded or branched, okay, as we shall see on. And lastly, they are numerous or large. For example, or fish. If you ever got a chance to see fish and gills of fish, each of those hair-like projections inside it is a gill filament, and that's where the gaseous exchange takes place. And there are very many of them, up to several hundreds of them on a single bar, and there are quite a number of bars on just one side and on the other side too. So that makes it very, very many filaments, and that increases the surface area over which gaseous exchange can take place. The more filaments we have, the more exchange that's possible to take place within that organism. And as we're going to see, mammals have alveoli as the specific parts where exchange takes place, and they're quite numerous, large numbers of them in every single lung, and we have two of those. So in some cases they are large, and in other cases they are numerous. Now, important for us to note is that this about blood capillaries does not apply to insects. Why? Because insects have an open blood transport system, meaning their blood literally bathes all the cells, all the tissues. Do they have blood? Of course they do, but it's not as red as ours. But they do not have this part of blood capillaries that don't supply to them. But still, the blood surrounds the tracheoles. Tracheoles, they appear more like this, and they dip inside the blood, because remember the blood is bathing all the tissues, so they are bathed also with the insect blood, and that makes the gaseous exchange process easier, because the blood is where the carbon dioxide is contained and where the oxygen crosses to.